LANs and WANs, local area networks and wide area networks. And more generally, this topic is about different types of networks. So we've talked about two main concepts for networking, switching and routing. Now we're going to move into some more details about individual networks. For example, the network that connects all the PCs inside SIT, or the network that connects our two campuses together. So what approaches can we use to build a network for serving, say, inside an organization or connecting multiple organizations together? So we'll first try and classify or categorize different types of networks, and we'll define what we mean by LANs and WANs as we try and categorize networks. So there are many different technologies for building computer networks. I think you know of some. You use Wi-Fi, that's one technology. You use your wired LAN, or sometimes called Ethernet, another technology for inside a small area. But there are many others that you use. You use ADSL, cable modems, satellite internet, and then maybe even on the occasion Bluetooth for forming a small network, even with just two devices nearby. And then there's some that you don't see. Some that connect, say, our campus to the rest of the world. Like, we'll talk about PDH, SDH, different fiber, optical fiber-based technologies, ATM and others. So there are many different network technologies. We can sometimes categorize them based upon different characteristics and compare them. So some of the ways to categorize network technologies are by transmission medium, a wired network versus a wireless network. So some technologies are wired, some are wireless. And there are advantages and disadvantages of each. Based upon the link configuration, some networks use point-to-point links. Remember, point-to-point, we have two devices and a link connects just those two devices. Point-to-multipoint, we can have multiple devices sharing that one link, like in wireless communications. So some network technologies use different link configurations. Some networks support fixed users, whereas others support mobile users. So Wi-Fi, for example, allows you to move and still access the network. A wired LAN, you're basically a fixed user. If I plug the LAN cable into my laptop, I can move my laptop a little bit, but I cannot go far. So it's considered a fixed network technology. Some networks are for us human users to access the network, whereas other network technologies are to carry the data of other networks. So we'll talk about core networks and backbone networks. I'll show you a slide that explains that more. And some networks cover or are intended to cover different geographical areas. Some are supposed to be used for communications across a small distance, centimeters, meters. Some are used for communications across a large distance. So we'll go through each of these, the first 3 or 4 quite quickly, and then a bit more on coverage area. Wired versus wireless. Which one's better? Well, there are advantages and disadvantages of each. With wired, when we transmit a signal across the wire, or even a fiber, if it's optical fiber, then usually that signal is contained inside that conductor or that fiber. So there's very little interference when you transmit a signal across that wire versus when someone's transmitting a signal across a neighboring wire. The result is that we can generally achieve very high data rates because there's very little interference. And it's easy to upgrade capacity. If you have ADSL at home, okay, anyone? ADSL? Yes, and what speed can you get download? What do you pay for? How many megabits per second? Anyone? 16 megabits per second, okay? So you pay this, whatever 800 baht per month and you get some download speed. Okay? And that link is from the telephone line. Okay? So you have one telephone line coming into your home and you get internet access via that one link. You can easily double your speed from 16 to 32 by buying another telephone line and having a second cable coming into your home. Okay? So in theory, it's very easy to upgrade the capacity by just adding a new link. Because with two links coming into your home, the transmissions across those two links will not interfere with each other because signals across cables usually are contained within those cables. So upgrading the capacity using wired networks is very easy. Similar, I want to connect my laptop to this PC. I can have a wired LAN, so a LAN cable that connects them. And with a LAN cable, I may be able to send at 1 gigabit per second. If I want 2 gigabits per second, what I need is a second LAN port on my laptop, and it's easy to buy a LAN card for the PC and plug in a second cable, and now I've got 2 gigabits per second. Very easy to upgrade the capacity. All right, not so common to do that for us end users, but say the links between different cities, between different countries, upgrading the capacity is quite simple. You just add new cables. With wireless, that's hard to do because with wireless, when you transmit, you interfere with others. So you can't just upgrade the capacity easily because the more people using it, the more interference and the lower the data rate. So it's not easy to increase the capacity of my link from my laptop to the access point. I can use different channels and so on, but on the same channel, I effectively cannot increase the capacity. So it's an advantage of wired systems. So generally, compared to wireless, better performance, higher data rates, smaller delay, predictable delay. With wireless, because of interference and varying conditions, sometimes there's interference from different sources, you generally get poorer performance compared to wired. Wired links are expensive to install in hard-to-access locations. You want to, SIT wants to upgrade the capacity from our campus to the other campus. So in theory, we can just add another wire, but if we need to dig another hole over the 16 or so kilometres between the two campuses, that's very expensive to do. Okay, if there's already an existing duct or hole under the ground that we can place our wire, that's okay. But if we want to build a new network, then digging holes under roads and under buildings and so on is very expensive. So adding wiring in many cases is quite expensive. Similarly, inside your home, maybe you want to have a network that covers all the rooms. Your home's already built. Putting in new cables is quite hard work. Either you need to run those cables along the floor and stick them on the walls, which no one likes the look of, or you need to put them inside the walls, which can be expensive to do. So wireless can be better in that case. Wireless is very convenient. Okay, we don't need to add those wires. Of course, with wireless, we also allow mobility. That's a key advantage of wireless communications. Whereas with wired, our device locations are fixed. So some of the trade-offs between wired versus wireless. So depending upon your requirements, you choose a network technology based upon the transmission medium. If you want mobility, then you basically need wireless. If you want high performance, but you don't need mobility, then wired may be better. What else? Link configuration. Remember, point-to-point is then we have one link, and at the two endpoints we have two devices, and they use that link just for themselves. No one else uses that link. So it's a dedicated link, meaning the performance for those two devices is generally high. It doesn't have to be shared with anyone else, the capacity, and predictable. So if I connect my two computers by a 1 gigabit per second LAN interface, then I'm pretty much guaranteed to be able to transfer at close to 1 gigabit per second all the time. But if I connect my two computers via point-to-multipoint link, like Wi-Fi, then the performance depends upon how many other people are using that link. So a point-to-multipoint link, we have multiple users sharing the one link. When I say link here, it doesn't need to be a cable. So I can talk about I have a link to the Wi-Fi access point, and everyone else uses that same link to the Wi-Fi access point. So dedicated performance is good for point-to-point links, but it makes it more inconvenient. If I want to now connect not just to this PC, but to someone else's computer, I need another link. And to each destination, I need a separate point-to-point link. And we'll look at some topologies in this topic that show some arrangements of nodes which are common. The problem with point-to-multipoint links, it's good in that multiple users can share the one link, very convenient, but requires some way to allow them to share. We've talked about multiplexing. Remember multiplexing? Allow data from multiple users across one link. In wireless links, it's referred to as multiple access. And usually we talk about multiple access or medium access control. Control who accesses the medium at what time. So a MAC protocol deals with allowing multiple users to share one medium. There are a few slides on that in this topic, but I think we will not get time to cover it today. Point-to-point, many wired links are point-to-point links. Some wireless links we can think of as point-to-point if we have highly directional antennas. So if we have antennas pointing at each other, then essentially they don't interfere with anyone else, and it's a point-to-point link. Point-to-multipoint, most other wireless systems which use omnidirectional antennas consider point-to-multipoint. Your laptop, when you talk to the access point, is using an omnidirectional antenna, and that's considered a point-to-multipoint link because not just does my laptop talk to the access points, so does everyone else's mobile phone and tablet in this room. Some wired links are point-to-multipoint. We'll see some examples in a moment. So, categorizing networks by transmission medium, by link configuration, by who accesses and uses the network. So we said we can distinguish between access and core networks. Let's try and explain this with this diagram. We have end users, the computers. So the human users are using these devices. For example, this access network, this cloud represents a network that I connect to. And similar, there's other people connecting to other access networks. So access networks are the networks which the end users directly connect to. But the way that large networks work is that we connect multiple access networks together via other networks. And those other networks we refer to as core networks. So these two access networks at the bottom are connected together by a third network, which we'll refer to a core network. And the distinguishing feature is that the end users directly connect to the access network. The core network doesn't have end users connected to it. The core network only connects to other networks. So we often have different technologies for access networks and for core networks. Give me an example access network technology. What's an example of an access network technology that you may use? What's an example of a network technology that you use which is considered an access network? network technologies. So think about some of the protocols that you use to connect to other computers. No, not HTTP, not TCP/IP. Think of the lower layers, physical and data link layer. How do you connect from your computer to another device? LAN. So LAN is the general name. Maybe the more specific name is Ethernet, an Ethernet LAN or a wired LAN. So that's one, what I say, network technology that allows you to connect to other devices. And it allows you to access a larger network. So we call that an access network technology. The computer is attached via LAN cable to some other device. A core network connects multiple access networks or other core networks together. And we may even talk about backbone networks. Maybe across a country we have a large network that connects many core networks together. And that the way that users communicate is that they send their data across their access network, and then their data traverses the core networks and maybe the backbone network, and then to another destination access network. We will see some examples of technologies used for core networks later in this topic. How many networks in this picture? How many networks? Where a cloud represents a network. How many networks? "13 networks." All right, you count the clouds, there are 13 there. Just in this example. Well, another way to think of it, there are 14 networks. There are 13 component networks, small ones, and then one large network by joining them all together. So we can think a network is this entire thing here. We can talk about networks of networks, or we connect different networks together to form one larger network. And that's essentially what the internet is. We have a topic on the internet, but in brief, the internet is many smaller networks connected together to create one large interconnected network, one large internet. So we'll see when we go into detail of the internet, it looks like this. Of course, much more complex. We connect many small networks together to form one large network. The last categorization is by size or coverage area. When we build a network, about how many meters does it cover? How far apart can the users be or the devices be when they communicate? There is no one definition of these, but I've roughly classified based upon centimetres, networks that cover in the order of centimetres, maybe hundreds of centimetres, metres, kilometres, and megametres. Megametres really is thousands of kilometres. So centimetres, networks that cover or allow communication around a person, your headset to your mobile phone. So that's a simple network. Maybe you use Bluetooth to communicate from the headset to the mobile device or to your watch. So sometimes called a personal area network or a body area network. Maybe some medical devices which are monitoring a patient in a hospital that can form a small network. Or between objects, my wireless keyboard, wireless mouse, my PC, and maybe other objects form a network between each other. Usually in the order of up to a few meters in distance. Some of the example network technologies are infrared, Bluetooth, and some newer ones, Zigbee and IEEE 802.15.4, and there are others. These last two are mainly used for connecting different devices to allow them to automate things. For example, we want to connect all the air conditioning control units and connect them to some other device so we can control them remotely. So we could use maybe Zigbee or 802.15.4 to wirelessly talk between the different air conditioning units to control the air conditioning. So small networks, and the acronyms BAN, PAN, personal area network is commonly used. We move up in size, covering meters, tens of meters, maybe hundreds of meters, covering homes, offices, buildings, even a campus in some cases. We have local area networks. That's the general name that we use to a network that covers a home or a building. Some specific instances of a local area network are a home area network. Sometimes we may refer to it specific for a home, which may have different requirements to some other locations. Or maybe you have, in a data center or in a company, you have many file servers you need to connect together to share storage. So you can hear people talk about storage area networks. So essentially, instead of having a set of hard disks in one computer, those hard disks are spread across many devices and they communicate across a network. And the main technologies that you come across are a wired LAN, and the general name is Ethernet. The formal name is IEEE 802.3. And wireless LAN. The general name is Wi-Fi, or the marketing name, and the formal name is IEEE 802.11. But there are others for more specific purposes, and some older ones, fibre channel, and there are many others. But those are the main two we come across. Moving up, connecting across cities, across countries, between countries, so across oceans, across a continent. So in the order of kilometres, hundreds of kilometres. We generally talk about a wide area network. So there will be different technologies that will be used to cover across such a large area, a WAN. If we're talking especially about cities, sometimes we refer to a metropolitan area network, but the more common one is a wide area network. So the technologies that we connect cities together and countries together are usually much different than the technologies we use to connect inside our home. Inside our home we may use Ethernet or Wi-Fi, but between Bangkok and Singapore we may use other technologies, and some of them we'll mention a bit more detail, but PDH, SDH, ATM, frame relay, satellite access, and there are many others in fact. So for long distance links usually, or large networks. This topic mentions a few details about the first three. Our next topic talks about Ethernet in more depth. Covering the globe, okay, covering the entire Earth, and sometimes we refer to as a global area network, or maybe just the Internet. So the Internet is an example of a network that covers the Earth. It really is made up of connecting many different wide area networks and local area networks together. So like in this picture, the Internet can be, think of many smaller networks connected together. If we go beyond Earth, we can connect between different planets and different objects out in space, satellites, spaceships and so on, and people talk about interplanetary networks. The main point is that the technologies that we choose usually differ depending upon how big the network will be. The technology we use for personal area networks is usually different from what we use inside the home, which is different again from what we use to connect between cities. In this topic we don't go through all of these technologies, but just be aware that we usually classify by, say, personal area, local area and wide area networks, and then the Internet as the global network. Questions on how to categorize networks. or anything on network technologies so far? WiMAX is a wireless technology for larger distance than Wi-Fi. So Wi-Fi generally covers, meters, tens of meters, maybe in extreme circumstances with very large antennas, maybe kilometers. WiMAX is an alternative really to your 3G wireless access. So 3G, there's a tower, a cell phone tower, or a base station, and you talk to your mobile phone wirelessly. WiMAX is similar, but there's some towers, and they talk to, say, to your laptop for long-distance wireless access, or talk to a device in some home. So WiMAX is wireless coverage over distances of usually kilometres, maybe 10, 15 kilometres. PDH, SDH we'll talk about, but are really technologies for connecting across cities using PDH using electrical cables. SDH mainly uses optical fibres. ATM and frame relay are networks which are usually formed across cities and across countries. For example, in the past and still in many networks, I think you know that with your mobile phone you connect to a cell phone tower or a base station. You see them around, okay? You see the towers in many locations. But then those towers connect via wired links. So AIS, for example, has towers all through the country, and those towers are all connected together via a wired network. And one technology to connect them together was ATM. It doesn't give you money, it gives you connectivity between different devices, okay? And frame relay is really an older technology than ATM for that. Any other questions on network technologies?
So why is WiMAX not so popular?
Why is WiMAX not so popular? So WiMAX is maybe considered as an alternative to using, say, 3G for wireless access across a large distance. Why is it not popular? Maybe for many reasons. It was new compared to mobile phone networks have been around for a much longer period, so people are used to the technologies and using them. It can generally provide, maybe 5 or so years ago, it could provide much higher data rates than your mobile phone, but mobile phone technologies have improved a lot recently. Now you can get up to 40 megabits per second, maybe 100 megabits per second to your mobile phone, which is matching WiMAX. So there's not much difference in speed now. Maybe it was due to the implementation. Everyone has a mobile phone. For WiMAX, you need a new chip, a new wireless chip in your device, maybe in your laptop, and there was a cost involved of creating them. Maybe the companies that built the mobile phone networks didn't support WiMAX so much, so there wasn't much support behind it. It's used in some cases, though. There are some large networks in the US that use WiMAX. Other questions on network technologies?
So what about the people?
What about
People, multiple input and multiple output.
multiple input, multiple output, MIMO? So maybe when you hear about different wireless technologies, WiMAX, maybe new mobile phone, new Wi-Fi technologies, they have, especially Wi-Fi access points, have multiple antennas. Okay, this one has 2, but it's very old, but some of the new ones have 3 antennas, and they're starting to support a technology called MIMO, M-I-M-O, multiple input, multiple output. The idea is that multiple input or multiple output is that you transmit out multiple copies of your signal, one through each antenna. So with 3 antennas, for example, when you transmit your data, you really send 3 copies of that signal, one via each antenna. And multiple input, there are 3 receive antennas. So they receive 3 different signals. And the idea is that with 3 different signals, they are separated in space, those antennas. So they're a little bit apart, a few centimetres apart. And the signals that are received are of the same data, but the signals are slightly different. They're received at different times because of different propagation delay and with different characteristics because of interference. And it turns out that it's easier for the receiver to process the received data when it receives, say, 3 copies of the signal versus 1 copy. And it can process the data better. As a result, you can send faster because it can handle processing at higher data rates. I don't know much more about it than that, but multiple input, multiple output is really transmit multiple signals, receive multiple signals, and the processor at the receiver is much smarter to be able to work out what that signal represents, and it allows you to send faster. So that's not related to, that's way out of scope for this topic, but interesting topic about wireless access. We're going to focus mainly on wide area networks and local area networks. The smaller networks often have similarities to local area networks. Different technologies, but some of the concepts are similar between LANs and PANs. So we will not specifically talk about the smaller networks. And really, most large networks can be similar to classified as wide area networks. So that's a simple classification. Wide area networks usually connect devices, as we said, across a large area, a large geographical area. Examples between campuses. So our campuses for SIT, we use a wide area network technology to connect them between office buildings, cities and countries. LANs within campuses, whether it's a university campus or a company, within buildings, within homes. Usually, wide area networks are owned and operated by some organisation that runs it on behalf of other people, on behalf of the users. That organisation is usually a telecom company or an internet service provider, an ISP. So the government telecom companies, for example, in Thailand, TOT, CAT, and I haven't listed the many different ISPs which run their own network. So these companies build a wide area network, they own it, they operate it, but then they lease or rent access to that network to the users, where the users may be different organisations, universities, companies, other internet service providers. For example, we want to connect our 2 campuses together via a wired network. SIT is not going to build a network between our 2 campuses. What we do is we lease or rent access to a network from some telecom company. So they already have the network connecting the 2 locations. They just, we pay per month for access to their network. With LANs, usually they're owned and operated by the organisation using the network. So the wired LAN inside our campus here, it's made up of cables, different LAN switches. That network is owned and operated by SIT. SIT built it and paid for all the equipment. It's inside the walls and the different rooms. And we are the user of that network. So that's one difference between WANs and LANs, and it has an impact on what technology can be chosen. If you own and operate and build the network, then you have more choice as to what technology to use. If you want to rent off someone else, well, basically you have to choose from whatever they will provide. And usually there's less choices of technologies. What else can we compare them? Although it changes a little bit more recently, but typically LANs have a higher data rate than wide area networks. One example is the SIT LAN. The wired LAN supports data rates up to 1 gigabit per second. So if I want to communicate, say, my office computer to another office computer inside our campus, I can send data up to 1 gigabit per second. But if I want to communicate from my office computer to someone out on the internet, I'm really limited by the link from our campus to the next location, our wide area network link, which may be in the order of tens of megabits per second. I don't know the exact data rate that we support. So I think the WAN link from Bangkari to the rest or to the next location is usually much smaller or slower than the internal LAN. Okay, so LANs are usually higher data rates than wide area networks. Because the local area network supports not just communications from me out to the internet, but also me to other locations internal. So it needs to support more data. But there are some exceptions to that. It's not always true. The last thing today we'll look at, again, generally with networks, some topologies which are common. We'll introduce a few, and then next week we'll give a few examples of wide area network technologies. I'll just mention 2 or 3. And then the next topic is on Ethernet, which is how LANs, wired LANs work. So we'll spend some time on that. And the last topic for this course is on the internet, which can be thought simply as connecting many different WANs and LANs together to form one large network. So let's finish with a look at some common topologies, how we connect nodes together in different networks. Remember, a topology is how we arrange nodes and links. So in the topic on routing and switching, we saw that example network topology of those 6 nodes and those links between them. That's a topology. So the nodes or devices, well, we have 2 different types of devices in a network. The devices which have data to send. So the data is created by some devices and sent to some devices. Sometimes we call them stations. So my laptop or my PC or your mobile phone can be called a station or a host or even an end node. So the devices that we use we'll refer to as stations, for example. But inside some networks there are other devices. Devices that the human doesn't use but is used to support the data delivery. We've already mentioned in switch networks we have switches. And we'll see similar, we will refer to switches, but there may be other devices like repeaters and hubs, some common names. The links are either point-to-point or point-to-multipoint. We will go through these 4 topologies over the next few slides with some pictures, and there's a hybrid topology which is combining them in different ways. So we'll go through them with more detail. First, when we want to build a network and we need to choose a topology, some things that we would desire are listed here. We should allow stations to communicate with any other station. I have a network to be built across our campus. We've got many PCs in offices, in lecture rooms, in labs. We'd like to be able to have any PC to communicate with any other PC. So that's a common requirement. We don't want to limit the network such that this PC can only talk to some of the PCs in the network. We generally want to allow anyone to communicate. Usually using point-to-point links is better than using point-to-multipoint. Remember we said point-to-point we can get higher performance than multipoint. So if we can, point-to-point links is better for performance. Maybe a conflicting requirement is that we often want to use as few links as possible. The more links, the more cables we need and the more maintenance and the more complex it is to install the network. So minimize the number of links. We would like a network that scales well, which means that if I build a network today in some arrangement, some topology, and then in next week I want to add a new network node, a new PC, it should be easy to add a new node to the network, a new station. Take little effort to build or upgrade the network. Often we like fault-tolerant networks. If something goes wrong on, say, one link or in one node, we don't want the whole network to fail. Okay, that would not be good. We want it to be able to tolerate some faults. For example, this PC has a link, a cable going to it, goes up through the wall. If the link fails here, maybe someone pulls out the cable or accidentally cuts the link, we don't want that to affect all the other PCs in the network. So we'd like to choose a topology that allows for fault tolerance. Or if some device fails in the network, we'd like the other devices to still be able to communicate. In some cases, we'd like to be able to quickly detect faults. If someone pulls the link out of this PC, maybe we'd like to be able to detect that that's happened automatically, so that someone who manages the network can go and fix it. That's not so much an important requirement for LANs, but in wide area networks, that's often very important. You have a link, or you have a network connecting one country to another. If there's a link that fails for some reason, we'd like to be able to automatically detect that and switch over to a backup link. So fault detection is important in some networks. So keep in mind these requirements of what we'd like to achieve, and we'll go through 4 or 5 different topologies which are common. First is a mesh topology. The example picture gives us 6 nodes, A through to F, and in a mesh topology, we connect each of those nodes to every other node via a point-to-point link. So there's a point-to-point link from A to B. So when A wants to send data to B, it uses that link. Point-to-point links are good for performance. The link between A and B is not used by anyone else. So they get the performance that the link offers. It's not shared. If A wants to send to C, it sends via a different link, and so on. So we get this full mesh connecting all the nodes together. This is with 6 nodes. How many links? Count the links. How many links in the network? Count the lines, or the links. Sure? Did you count to 30? It's not 30. Can anyone count? If you look at those links, I think you'll find there are 15 links. There's one from A to B, from A to C, A to D, A to E, A to F. That's 5 links. Then from B, there's one from B to A, but we just counted that. Then B to C, D, E, F, so another 4, so that's 9. Then another 3 for C, that's 12. Another 2 from D, it's 14. Another 1 from E, that's 15 links. This is a simple example. Now consider SIT, all the lab computers, office computers, lecture computers, maybe 1,000 computers. How many links needed? So imagine we have 1,000 computers we want to connect in a mesh topology. Turns out the equation is the number of nodes times by the number of nodes minus 1 divided by 2, which is with 1,000 computers about 1,000, or it's 1,000 times 999 divided by 2, which is about 500,000. So if we want to connect all our PCs in a mesh topology inside SIT, we'd need 500,000 cables going across the campus. Just wouldn't be possible. And also, each node has 5 cables coming out of it. So we've got 5 cables plugged into each node. Again, if I have 1,000 computers, I'd need 1,000 different cables plugged into this PC. Again, not possible. Mesh networks, full mesh networks, are only used in small scenarios when we have a few nodes to connect. Usually not in LANs, mostly in small wide area networks. It becomes too complex, too many cables, too many links as the number of nodes increase. But good for performance because every pair of node gets a dedicated link, guaranteed performance. An extension or a subcase is a partial mesh. Don't have links for all pairs of nodes. Less links, that's good, but the problem is A can't talk to F. Okay, without a link from A to F, it cannot communicate with F, unless there's some way that A, for example, could send to E, and then E could forward it on to F, which is really what our switching approach does in our general networking. So such a topology is commonly used for large networks like wide area networks. You cover the country, you have links between many different nodes, but not a full mesh, just a partial mesh. Not used in LANs, for example. A bus topology. You probably studied buses in terms of computer hardware. We communicate across a bus. Similar in a network. We have our 6 nodes attached to a bus. This solid black line, think of that's the communications bus. And the way that a bus works is you transmit onto the bus and the data travels across the bus. And you can think, for example, if A transmits data to D, it transmits the data onto the bus and the signal carrying that data travels across the entire bus in both directions. So in fact, every other node can receive that signal. The way that it works usually in networks is that A transmits to D, it creates a frame and sets the destination address to be D, sends it onto the bus delivers it to everyone. B, C, E and F ignore it because they are not the destination. D takes a copy because it is the destination. This bus link is a point-to-multipoint link. One node transmits, multiple receive. So it's in fact a shared link. And that's a disadvantage in that the performance depends upon how we share that amongst the multiple users. Bus topologies were used in early wired LANs. So maybe 15 years ago now that many of the wired LANs inside campuses and inside offices used a bus topology. Basically, there was a cable that passed all the PCs, and the PC had a special attachment on the bus, on the back that connected to that one bus cable. So there's a single multipoint link connecting the stations. It's a point-to-multipoint medium. A transmits, everyone receives. What else should we stay here? It's generally easy to install compared to the mesh. We just need one long cable that bypasses all of or goes past all the stations. So if I want to connect all the PCs in the building, then we need a cable that passes all of those PCs and they essentially connect onto the bus. If we want to add a new one, we just need to make sure that that bus passes that new node. The problem with this in terms of performance is with point-to-multipoint, we need some way to allow the users to share the medium. The problem is if A transmits and at the same time B transmits, the signals for those transmissions will interfere with each other and no one will receive the data. So we need some way to share, and that reduces the performance. If the bus fails, no one can communicate. That's a problem as well. So if there's some error on the bus, then nothing will work. A similar topology is take the bus, but join the 2 endpoints together. Take the dots here and join them together, and you really get a ring topology. It can be either a joined bus, or we can even just have point-to-point links between each pair of nodes to get this ring topology where A transmits the data. You can think the data is placed on the ring and passes all the way around and back to A, and then no more transmissions occur. And again, if A transmits to D, the destination address is included in the frame, and the frame is ignored by F, E, D takes a copy, and ignored by C and B, and really you can think A removes it from the bus. So a ring topology, we transmit our data all the way around the ring. Whoever is the destination takes a copy of that data. It's very good if you want to be able to send data to a selection of the nodes. You want to send data to both D and C. Then since the frame passes all nodes, it's very simple, and D and C take a copy. It usually moves in one direction, but you could have a bidirectional ring. That is, you could basically have two cables. So if you have a single direction, then you have some performance problem. If A wants to send to B, it needs to go all the way around the ring. But a way to overcome that is to have a second cable that goes the other direction, and choose the one that works best. It's not so common in LANs today. It was used in old LANs. So there was something called token ring. But in wide area networks and across cities, metropolitan area networks, it's still common where there are multiple rings in both directions, and it supports fault detection quite well in that if there's a fault, if we send data, if there's a fault between E and D, this portion of the link has a fault, the data gets to E and D doesn't get the data. Well, we've identified the portion of the network that has the fault, because if E got the data and D did not, then we know that the fault is between E and D. That's very useful in large networks across cities and between countries, because once you detect a fault, then you can switch over to a backup link. And in large networks, they have multiple rings, so essentially multiple cables in both directions. It's still a point-to-multipoint medium in that we need some way to share the medium. If two users transmit at the same time, they'll interfere with each other. We'll come to that ways to share the medium next week. The main one used in LANs today is a star topology. We connect all our stations to some special central node. It's not a station. We'll often refer to it as a hub or a switch. And we usually use point-to-point links from the station to this central node. And if A wants to communicate with D, A transmits to the central node, and it's got a dedicated link to do that. No one else can use this link. And that central node then recognizes from the destination address, okay, it needs to go to D, so transmits across this link to D. So we now introduce a new device which supports the communications. And this is really what's used in most wired LANs today. So this PC has a cable going through the walls down to the third floor. In there's this central device, a switch. And that central device has many cables going into it, one from each PC inside the LAN. And you have that at home. You may have your home ADSL or home router, and on the back there may be 4 ports. Sometimes you see those yellow or blue ports on the back, and which means you can plug in 4 LAN cables and connect, say, 4 laptops or 4 PCs to that central device. That's the switch or the central device. If you want to add a new node, then you just connect to the switch, the central node. So add a new link. So that's quite simple to add a new one, as long as this central node has enough ports to plug in a new cable. If node D fails, it doesn't affect the other nodes. All the other nodes can still communicate with each other. If the link from D to the central node fails, then again all other nodes can still communicate. So that's good in terms of fault tolerance. But if the central node fails, the whole network fails. And that's bad with respect to fault tolerance. So there's a high dependence upon this central node. That needs to be reliable. That's used in most LANs today, and in the next topic on Ethernet we'll see a few more examples of how that setup is used in a real LAN. So a quick overview of some common network topologies. Some of those topologies require sharing the medium. So the next part is upon how do we control who has access to the medium at what time. That's next week, and then we'll summarize with a few example network technologies and then look specifically about Ethernet.